And so how are we to visualize this union theorem for our category of functions? Well, it's really quite simple. So here's an example. We have an object X, a bouquet, and we have these sub-objects, little a and little b, and then little a union little b just contains each vertex in each loop, which is contained in a or b, and that's all. Okay, so union's a pretty simple kind of thing in set to the power of c, really, although or in general in topos theory is sort of more complicated than and, which is a kind of funny thing, really. But so how is or defined in general? Well, there's various different ways to define it. I prefer Goldblatt's way of looking at it. So this is for a general topos. So if we take our sub-object classifier omega and we form the coproduct of it with itself, then we can find this arrow from that to the product of omega with itself. Now, this is the coproducty pair of T exclamation mark omega, comma identity omega, and identity omega, comma T exclamation mark omega. So we form this arrow, and this arrow goes from omega plus omega to omega times omega. Now, we want to actually get a sub-object, so we take the image of this arrow here, and we call that alpha. Now that is going to be a sub-object of omega times omega, and then we can define or as the classifying arrow of alpha. Okay, so that's how it's defined. And it has some nice relationships with union. So in particular, if we have sub-objects A and B of X, then of course this producty pair chi A, comma chi B is going to go into omega times omega, and then we have this or arrow taking that into omega. And so we actually have that if we compose or with chi A, comma chi B, we get the classifying arrow of A union B. So this is all generally true. Now, the theory about OR goes pretty deep, and it involves some fairly intricate notions in topos theory to understand it properly. But just to point something out, and then I'm going to get onto an example, and we're really going to see what OR actually looks like. Here's the thing I wanted to point out. The thing is that you see these two kind of arrows from omega to omega times omega, which we put inside our coproducty pair when we're forming this black arrow. Well, these are actually monomorphisms. Okay, so this is a monomorphism from omega to omega times omega, and so is this. All right. And so really, if we compare with our previous kind of definition about union, then we say, okay, well, this alpha here is just the image of the coproducty pair of these two monomorphisms. And so I suppose we can write alpha as the union of these two monomorphisms. Anyway, like I say, I'm about to illustrate how we can actually construct OR using this kind of method for our category of functions. And of course, we know how to find images, we know how to do stuff with products and co-products in general with set to the power of C. So there's nothing to stop us being able to make this kind of OR arrow, being able to compute it for any category set to the power of C. But I just want to point out this conjecture, which I haven't proved yet, but who knows, maybe I'll put a proof or disproof to this in the description to this video in the future. But anyway, I guess that in set to the power of C, for an element alpha comma beta, an E-type element of omega times omega, I guess that doing the ETH component of OR on alpha comma beta gives us alpha union beta, where we're thinking of this alpha and beta as sub-objects of Hom E comma blank. Anyway, let's quickly get onto an example where we actually see what this OR arrow looks like. So we're going to do this computation. The first thing we're going to do is work out what this kind of black arrow looks like in this category of functions. Well, okay, so I've drawn it in green instead of black in this picture, but it's this arrow from omega plus omega to omega times omega, this green arrow, and it is this. Okay, it is the co-producty pair of t after exclamation mark omega, comma 1 omega, comma 1 omega, comma t exclamation mark omega. And this green arrow is the co-producty pair of t exclamation mark omega, comma 1 omega and 1 omega, comma t exclamation mark omega. So here it is drawn here. You see I've got omega plus omega here. So it's just like two disjoint copies of omega. The ones on the left are indexed with zeros, the ones on the right are indexed with ones. And so when we're sending arrows from stuff on the left, according to this, we send the loop to the pair which is true, what the loop is. So for example, this one here is psi m, so it gets sent to psi true, comma psi m, and so on. And when we're dealing with stuff on the right, we use this bit, so we send it to itself, comma true. Okay, so for example, this is sent to psi m, comma psi true. And so we have this arrow into omega times omega, and then we want to find the image of this. So we just want to find all of the stuff that get in omega times omega that has something sent to it under this green arrow. So we compute this image of this arrow, which is what we're calling alpha. And you can see I've drawn it as a sub-object here. And then we just want to compute, oh, and note, if you look at this, it's interesting. Look at the things which are actually in this sub-object. They're all the things that have something true in them. Okay, so this has got a true in it. This has got a psi true in it. This basically just holds all the loops which have something true in them. Okay, and then we find the classifying arrow of this, and that is our OR arrow. So OR is the classifying arrow of alpha. So it sends everything that's in this sub-object alpha to this true loop. And then we can work out, these loops which are coming out of the vertex, a vertex which gets sent to true, but which themselves are not in alpha. They just get sent to this kind of M loop. And then any loops exuding from a vertex, which is, and any vertex, and any loops exuding from a vertex which is sent to false, themselves are sent to false. So false, false gets sent to false, stuff inside alpha gets sent to true, and these other kind of hanging on loops get sent to M. And then it does seem that this conjecture is holding up. For example, anything which has a true in it, if we think of these as sub-objects of harm e comma blank, if we form a union, that gives us the full sub-object of harm e comma blank, so these do get sent to true. This thing here with two m's gets sent to 2m because the union of m with m is just m. Similarly, with these ones, the union of false with m is m, as we have here, and then this one is the union of false with false, which is the empty sub-object, so it's sent over here. So it looks like our conjecture is holding up in this case. But anyway, we can always compute an OR arrow by following this kind of procedure in set to the power of c. And like I say, I think there is more to discover here, but there's just so many things going on to do with these kind of logical operations of set to the power of c. So sometimes we have to kind of put something aside and say we're going to return to it later.